Good morning, everyone. I'm happy to be here, and particularly considering the previous talk, which already touched on a few of the points I also have in my slides. I'm really happy. This was a great talk, and hope I can build up on it a bit. So what I want to do today is just show you a bit of what we at KIT and within our network are doing to support research software engineers and research software engineering workflows on our high performance computing systems, which we have at KIT. Now, first, a tiny bit about myself so you can sort of figure out where I'm from and what I'm actually doing. So originally I started off with a PhD in physics, where I was what nowadays would be probably characterized as a research software engineer, at least part-time research software engineer. And since then, I've moved towards the IT infrastructure part, where now I'm a team leader at Sternbuch Center for Computing for Software Sustainability and Performance Engineering, which is a team located in our high-performance computing department with close ties to also the other departments at Sternbuch Center for Computing and in general at KIT within Helmholtz and within the state of Baden-Württemberg. Now, Sternbuch Center for Computing itself is the information technology center of KIT, which means that on the one hand, we are the IT service provider with all the, let's say, mundane IT services you would expect, like network, storages, cloud provider, and so on and so forth. But at the same time, we're also a center for data-intensive computing and analysis of large-scale data. And in all of this, we are not only providing the IT services and the research equipment, but we are also actively pursuing research in these fields, offering teaching for students and partners, and contributing to innovation in those fields. And when we come back to the high-performance computing world, actually since 2021, KIT is a center in the so-called National High-Performance Computing Alliance. And for those of you who are not familiar with the high-performance computing world, the National High-Performance Computing Alliance is effectively, since last year, the funding body for the academic tier 2 high-performance computing on a national level within Germany. And for KIT, within this alliance, our focuses are, among other things, on expert level support for the domain scientists using our high performance computing systems, but at the same time also towards software sustainability and towards enabling the research software engineers and the scientists towards a sustainable software development and usage on our clusters. Now, I've talked a lot about KIT already, and now just to give you a very brief overview, I'm not going to go into too much detail about the clusters which we have at KIT, and there's actually two high-performance computing clusters which we have. You can see that here on the lower right-hand side, this pyramid, that's the high-performance computing environment in the state of Baden-Württemberg, and there are two blue boxes there. That's the two clusters in Karlsruhe. On the one hand, the so-called BW Uni cluster, which is a lower level high performance computing cluster in Karlsruhe and part of the high performance computing and data intensive computing strategy in the state of Baden-Württemberg. It's a cluster which is designed for general purpose computing and specifically also for teaching purposes within the state of Baden-Württemberg. And it really has a low entry burden or low entry requirement, which means that essentially any researcher of one of the stakeholders of this cluster, which effectively are all the universities in the state of Baden-Württemberg and a few universities of applied sciences, can very easily get access to this cluster and have modern high-performance compute capabilities available to them. Hardware-wise, in this system, we're talking about a very standard system. So that means we have about 32,000 CPU cores and around 150 NVIDIA GPUs. Nothing spectacular on that side, just an ordinary high-performance computing system. If we then move up one tier, this is our newer system, the Hochleistungsrechner Karlsruhe, which is one tier higher than the BW Uni cluster and specifically part of the National High Performance Computing Alliance. In this case, we have a modern hybrid system with around double the number of cores compared to the BW Uni clusters, around 60,000 cores and around 700 NVIDIA GPUs. And of course, as usual for high performance computers, very good interconnect and reasonably sized background storage, in this case around 16 petabyte for all the data of the scientists. If we look at the sort of global scope, the system here peaked around rank 13 in the most energy efficient systems in the world, and this is really something we are very, very proud about, because we really want to focus on enabling scientists to also perform energy efficient research and not just burn as much energy as possible to achieve the goal and be in a sustainable research environment. And the whole system is now available since a bit more than half a year, since the 1st of June 2021, for scientists within Germany on the national level, as I've mentioned before. Now, these two clusters, they are all relatively standard. You've heard before, I've mentioned that they do all have their CPU power, and they do all have some form of NVIDIA GPUs. And what we are thinking about was, how can we provide additional value for researchers and for software engineers who are working with our high performance computing system? And what we came up with was our so-called future technologies partition, which you can see here in the sketch with the yellow border. And this is essentially our means of providing access to non-standard high-performance computing hardware. So, for example, currently we do have a couple of ARM CPUs available, we do have AMD GPUs available, and we do also have, specifically for AI workloads, we do have a very dedicated hardware called GraphCore IPUs which are specifically designed for AI workflows. And our goal here was to enable research software engineers to already have the possibility to look at these non-standard hardware and this often then also, of course, breaking changes which are coming with using this type of hardware, and in that sense prepare for the future for systems which might be available in the next generation of HPC systems, or if you move to another cluster in the future, you might encounter these, and then you can already get prepared, test your software, and maybe also benchmark your software on these systems to see how well the software works. Now, taking one step back, I wanted to talk about the way we support research software engineers on our high-performance computing systems. And for this, I first want to give you a bit of a personal view, and those of you who have been in the workshop on Monday will probably remember this slide. So this is a bit of a personal view on what the challenges are in traditional high-performance computing when it comes to using the clusters and offering new services to users and to research software engineers. And typically what you'll find is that the clusters are quite regulated, which means you have strict access requirements for users. You have strict code of conduct, what you're actually allowed and not allowed to do on a cluster. You have the clusters which are typically quite secluded. In this case, I mean, network topology wise, which means that, for example, you do have to use certain proxy hosts to access the general purpose internet. Sometimes you can't even access the general purpose internet at all. Sometimes it's only such that you can access the cluster only from a very, very limited network range. And all of this ties into making it a bit more difficult to work with the high performance computing clusters and to offer the general services on these high performance computing clusters. And last but not least, specifically when it comes to offering services which are tailored for a specific use, the clusters are typically designed to be well utilized, which means that there's little to no space for intentionally idling resources which are just waiting for a very, very specific type of workflow. So you really have to put that together with how the cluster was designed and with the ordinary work which is happening on the clusters. Now, the good thing is, if we look at sort of the recent examples, maybe the past 5 years or so in high performance computing, you can see that there are very many trends towards modern services and access possibilities and usage possibilities for high performance computing clusters. And before, you've already heard some of them. Support for containers is definitely a huge thing on HPCs nowadays, which essentially allows the users and research software engineers to work in their own environment, independent of or to a large extent at least, of the software stack, which is pre-installed on the high-performance computing system. But at the same time, we can also mention, for example, interactive high-performance computing via Jupyter, which is, of course, largely driven by the data analytics and machine learning community. Now, services focused at RSE, which is what I originally put into the title of the talk, is something which we've also heard about in the previous talk, and which, at least from my perspective, is more and more being realized also within the high performance computing world, that there are research software engineers, and that research software engineers also in the high performance computing world do have certain requirements and certain tasks which they commonly execute. And in this case, we do have, for example, the continuous services, which we have heard about before: continuous integration, continuous testing, sometimes continuous deployment, which are very, very commonly used by research software engineers. And this concept is reasonably adaptable to high-performance computing environments. And as such, for us at KIT, we've decided that this is a really good starting point to have a look at such a service, to try to figure out how we can offer these types of services on a high-performance computing cluster, taking into consideration all of those limitations and challenges which I've mentioned before, and then find ways to address these challenges. Now, some of you might be wondering, why should we use such services on high-performance computing clusters? Aren't the public providers, like, for example, GitHub Actions or any sort of self-hosted runners, aren't they enough? Do we really need that on high-performance computing systems? And here I just want to focus on the comparison to these publicly available providers, like, for example, the GitHub Actions. And if you look at them, first of what you will realize is that you only have a limited amount of resources which you can get, and for all of the remainder, you'll have to pay extra if you want to use more than those resources. You typically only have access to a set of standard hardware, which means typically just some type of CPU. Sometimes you don't even have a very direct control over what type of CPU exactly is available to you. And last but not least, of course, when we're talking about software which is designed to use high-performance computing systems and later on to run on high-performance computing system, and one thing which you cannot easily test on these public providers is, of course, the integration with the whole software stack on the high-performance computing system, starting from, for example, the batch system up to interconnects, MPI, and so on and so forth. And all of this is very tricky to test on the public public providers for these services. And another point which I don't want to talk too much about now, because this would be a topic for an entire talk on its own, is that on these public providers, you typically do not really have any guarantee for the performance, which means if you run the same type of test 2 times, you'll find that one time it runs relatively fast, and another time it runs relatively slow. And if you want to, for example, evaluate the performance of your software, of your code, in a continuous method. For example, every time you introduce some new feature or do some refactoring, you want to test the performance, then you cannot do this on the public providers, but you need some sort of reliable performance where you can then actually perform the comparison too. Now, what we at KIT have been doing in this direction is that, first off, we've tried to think about what exactly do we want to achieve, whom do we want to offer these services to, and what might be possible challenges in this sense. And the easiest answer to a question to answer here is, whom do we want to offer these services to? And in our case, we've simply decided we want to offer that to all of our users of high performance computing at KIT, because for one, the clusters are already set up very, very similarly. And on the other hand, we can reach a wide range of users of these clusters, really from the sort of high or mid-end high performance computing users up to the very low end, having really the low entry requirements, and can really reach a wide range of researchers and of software engineers. And at the same time, with the future technologies partition, we of course also decided that we want to offer an as large as possible range of architectures and technologies to really facilitate this testing and evaluation against different architectures and technologies. Now, challenge-wise, what we've identified is that naturally users who are already using those services outside of the high performance computing world, if we want them to adapt to our service which we are offering, then we'll need to have something which at least looks and feels similar to what they're used to. So we don't want to put very high entry hurdles in there, tell them that they need to do something very, very different from what they used to do, and in essence, just have an easy integration into already existing projects. In the best case, just having something like a drag and drop replacement. At the same time, something that's important for the high performance computing world is that the users, of course, expect fast responses whenever needed. So for example, if you think about your everyday CI workflow and you have something which is tested, for example, on every commit, it's just to be sure that everything still compiles or all the tests are running after every commit, then you don't want to have to wait for several minutes, hours, or even longer until this job starts on a high performance computing node. But instead, you want to have a relatively fast response within just ideally a couple of seconds or maybe minutes to your continuous integration workflow. And at the same time, you might have greatly varying resource demands. We've heard it in the talk before. Sometimes you just do a simple test, and on other times you really need to run more extensive tests and really use more compute power for just a single test. So this is challenges which we have to address here. And for us, this simply meant that we cannot offer just a single monolithic service for the research software engineers and for the users, but we have to really take these points into account and offer a more diverse service. Now, what we've done is we started off with the way we wanted to offer the integration into known projects, and that is we've started off with the GitLab runner. It's, for those of you who have been using it, it's certainly are well aware of this. It's relatively easy to include into any GitLab project. It doesn't need to be a GitLab project specifically on the KIT GitLab or on any very specific GitLab, but it can be essentially on any GitLab around the world. It has known interfaces and configurations, which are at least relatively simple to understand and are also very commonly used also outside of the high performance computing world. And if you do that, then on the right hand side, you can see just a sketch of how this might look like with, in this case, 3 different GitLab runners on our HPC systems for different types of architectures, which you can just have available within your within your project in GitLab. The other part, which we've also heard before, is container support. If you look at the outside worlds, in quotation marks, compared to high performance computing, you'll typically have Docker. This unfortunately is not available within the high performance computing environments, at least within none that I'm aware of at the moment. And instead, what we typically do is we offer either Singularity, or in our case also En-root, which is a different type of containerization tool. And the problem here is that, quite simply, the GitLab runner is not natively set up to use this. It's just set up to use Docker. So what we do is we provide custom executors for our users, which lets them easily use the Singularity or En-root compared to Docker when they just specify a given container image within their CI job. The other part, which I've mentioned before, is the reaction speed and resource demand. And what we've simply done to cancel this, or to work on this, is that we've offered different service levels for our continuous integration services. On the one hand, we have a level where the continuous integration job effectively runs as a standard batch system job in our cluster for the high performance computing system. And this is, of course, suited if you have a very high or relatively high resource demand, while at the same time you can live with a certain medium to low responsiveness, which comes with the trade-off of using the batch system. And on the other hand, what we also offer is we offer a shared node for all of our users of this service, which they can all use to run GitLab runners on, and to really commonly use this node as a shared resource, which then, of course, comes with the trade-off that you do only have a relatively low resource availability for you. You do have to share them with the others, but at the same time, you get the very, very high responsiveness that your job essentially starts running off immediately on this shared node. Now, all of this is, of course, just some, let's say, early implementations, and we're well aware that there are certain limitations to this. The most obvious one is that one which we cannot very easily work around with, which is that you do need to have some certain type of access for our high-performance computing clusters, for example, compute time proposals, in order to use the service. But, and that's the more important point about this, you also need to already take this into account when applying for a compute time proposal, because effectively the usage of resources within the service will be accounted towards your project pledge. And this then means that you, when applying for compute time, already need to at least ballpark how much resources you will need for the continuous integration. The other aspect is that the integration here is, of course, no drag and drop usage. If you paid attention before, you've maybe figured this out, that every user needs to set up their respective GitLab runners on their own effectively with some help from our side. There currently are no shared runners where you can just have them available in a certain GitLab and you can just select them and it runs on one of our clusters. But really every user has to do this on their own at the moment. And this, of course, is a certain hurdle when it comes to using our services. However, to sort of countermand this, what we've done is we've, of course, do have some documentation. We are constantly working on improving this and, of course, also on training our users. So if there is interest in this from one of the users, we do offer training courses, and we do also offer the possibility to go into small groups and discuss possibilities of using the service for their respective project, which hopefully on our end will help ease the transition process into the service. And last but not least, I should also mention that this is, of course, something which is not just KIT. I've mentioned the National High Performance Computing Alliance before. There's also projects within the National High Performance Computing Alliance which are working towards this and towards enabling such services also in that scope.